Today we are going to discuss another approach to circuit analysis when the methods that we have discussed earlier, namely replacing resistances or different resistances appearing in circuits by their equivalent resistance and reducing all these resistances into a single resistance, so that reducing the circuit into a circuit which consists of one electromotive force and a single equivalent resistance. When this doesn't work, and in many cases it doesn't work, there are other methods to analyze the circuits. And today we are going to discuss one of these methods, which is based on two rules, and these rules known as Kirchhoff's rules. These are two rules, actually two simple rules, and one of them reflects, as we will see, the conservation of electric charge, and the second one reflects the conservation of energy. So let's start with this circuit, and we want to analyze this circuit. In other words, we want to find what is the current in each of these resistances. Okay, this circuit, as you can see, consists of two electromotive forces and three resistances. Well, first of all, the first question is, are these resistances connected in series or in parallel? If you look carefully, you might be tempted to say, well, these are all connected in parallel because they are drawn parallel to each other. But of course, a closer look tells us now this is not true. It's true that this resistor, the 6 ohm resistor and the 9 ohm resistor, are connected in parallel because the potential difference between these 2 points and these 2 points is the same. That's true. But if you look at this resistance, this is not connected with the 6 ohm, neither with the 9 ohm on parallel, because the potential difference across it is not the same as the potential difference across this, because the potential difference across these 2 points here is, when you look at it from here, is equal to the potential across the resistors plus the potential across this 18 volt electromotive force. So the potential difference across the 6 ohm and the 3 ohm is not the same, and so they are not connected in parallel. So this is why you cannot reduce this whole thing, these three resistances, into a single equivalent resistance. It's impossible. Another thing is that in this circuit we have two electromotive forces. And what we have learned so far was to analyze a circuit when we have only a single electromotive force. So we need probably a different approach. We need to apply a different approach to analyze this circuit. Okay, so what is this approach? This is based on applying Kirchhoff's rules. And Kirchhoff's rules, they are simple two rules. The first rule is called the junction rule, and it says that at any junction, the sum of the currents must equal to 0. The second rule is called the loop rule or the voltage rule, which says that the sum of the potential differences across all elements around any closed circuit loop, any closed loop in any circuit, must be 0. Now we will look at each of these closely, and we will analyze it, try to understand the basis of each of these rules, and then see how we apply it to analyze circuits. The first rule is the junction rule, which says sum over I on a junction equal to 0. Let's first define what we mean by a junction. A junction actually is a point in the circle where you have more than 3 branches leaving that circle. So that point. So a point here, as you can see, this is a part of a circle, in a circuit, you will have like 3 branches or 3 lines leaving this point. Okay, so this is a junction. If you have only 2, it's not a junction. So it's a point where the current branches. So this is a junction. It's a point where current branches. Now, this rule says that the sum of the currents at this junction should be equal to 0. Okay, and well, we have a sign convention here, and the sign convention here is that what is coming into this junction is taken as positive. When the current is coming into the junction, it's taken as positive. When the current is leaving the junction, it's taken as negative. So what does this say actually is that I1 minus I2 minus I3 equal to 0, or I1 equals I2 plus I3. Well, if there is no charge storing device here, then this is nothing but what? This is conservation of charge, because the charge will not disappear. Okay, so what the charge that reaches this junction, okay, when the current comes into this junction, and the current that leaves this junction must be split into these. This current must split into this current, and conservation of charge requires that the sum of these two currents is equal to this current. This is exactly, like you can think of this as, when you have water flowing in a pipe and this pipe branches into two pipes. Evidently, if you find the amount of water or the flow of water here and here should be equal to the flow of water into this point. Okay, so this is a reflection of the conservation of charge, and keep in mind the sign convention. When the current is coming into a junction, we give it as a positive, we consider it positive. When it's leaving a junction, we consider it negative. So here, this is how it looks. Now, before we move to the Kirchhoff's loop rule, let's remind ourselves with what we already learned about what is the sign of the potential drop when we cross a resistor or electromotive force. So, for example, here I have a resistor, and delta V always here means VB minus VA. Okay, VB minus VA. So, when VB minus VA, when you are moving, when the current is flowing from A to B, okay, so when you move from A to B, in this case, along the direction of the current from A to B, then VB minus VA, in this case, will be negative, because the current flows in the same direction of the electric field, and when you move in the direction of the electric field, you are moving through a potential drop. Okay, so always when you transverse resistor along the direction of the flow of the current, then you are moving through a potential drop. In other words, this end minus this end, the potential of this end minus the potential of this end is negative. Now, on the contrary, if the current is flowing in the opposite direction and you are transversing the resistance in this direction, in other words, you want to find again VB minus VA, so you are moving in this direction, then in this case, this potential, this point is at higher potential with respect to this point. So VB minus VA in this case, which is delta V, is plus IR. So this is the direction that you transverse the resistance in this case. Okay, you want to find VB minus VA, which is the delta V, when you are moving in this direction, but you are moving against the current, so in this case, VB is at higher than VA, so this delta V should be positive. Now, the same applies to an electromotive force. When you are moving from A to B in this direction, then VB minus VA, the potential difference of B with respect to A, VB minus VA, in this case, when you are moving from A to, in this particular case, it is positive. Why? Because you are moving from the lower the negative terminal to the positive terminal, and inside the electromotive force, we have seen that the electric field in this case is in this direction, so you are moving against the electric field. Electric field inside is from the positive to the negative terminal, and so you are moving against the electric field, and so you are moving in a potential rise. Now, and the contrary applies when you are moving from the positive terminal to the negative terminal inside the battery. In this case, you are moving in the direction of the electric field, and so when you're transversing it in this direction, then this point is at lower potential with respect to this point. So VB minus VA in this case is negative. So we come now to the loops, the loop rule. We have seen this circuit before, and the loop rule says the sum of the potential differences across all elements around a closed circuit loop is equal to 0. And let's apply, and we write this symbolically in this form, that the sum of delta V is equal to 0. Now, what does this mean? Well, a loop is any part of the circuit that you can traverse and come back to the same point. Okay, so a circuit might have, as we will see, might have 2 loops, 3 loops, multi-loops. So there can be any number of loops in circuits in a circuit. So any part of the circuit where you can start and go staying on the circuit, come back to the same point is called a loop in that circuit. So here, for example, this is a single circuit, a single loop circuit, because there is only one loop where you can, which is this loop in this case. Now let's apply this voltage loop to this circuit. Here, in finding this sum over a closed loop, you can start at any point on that loop, given that you come back to that point. So for example here, if you start at point A, and we are assuming that the current is flowing in this direction, so the current is flowing clockwise in this loop. And as you can see, we have noted earlier, and according to the just rules that we have just reminded ourselves, the sign conventions that we have reminded ourselves with in the previous slide, that if you go from A to B, then you are going through a potential rise. And so the potential delta V between A and B, that's VB minus VA, as you go from A to B, okay, in this case is positive. So when you go through this loop starting from A, you first cross this circuit element and you have a delta V which is positive. Then here, when you move through the resistance, which is the internal resistance of the circle, you are moving with the current. So when you traverse the resistance, small r in this case, the internal resistance, you are going through a potential drop. So delta V here is negative. VD minus VC is negative because you are moving along the current. So we have here a positive, we have here a negative. Continue, there is no circuit element here, so there's no potential difference here between these 2 points. So VD and VE are the same potential. Now when you cross from E to F, there is a circuit element which is R. Again, you are moving with the current, so VF is smaller than the potential of F is smaller than the potential of E, so VF is smaller than VF. So as you cross delta V in this case, which is VF minus V, is negative again. Now you come to F, then there is no potential drops here because there is no circuit elements, and you come back to A, you have completed the loop. So what the loop rule says is that if you add up these potentials, you will get 0. And this is evident here because we have a positive here and we have a negative here, a negative here. So the sum of those two negatives is equal to the sum of this positive. Now we have seen this before actually when we talked about the electromotive force in a previous video. And what we said is that when we have derived the basic equation of the basic circuit in this case, which was E equals I small r plus I capital R. If you check previous video, we have derived this result. And we have said this is a reflection of the conservation of energy, because it says that the potential energy provided by the electromotive force is equal to the energy, thermal energy dissipated in this internal resistance and in this load resistance. Okay, so this fact is just a reflection of conservation of energy. This graph shows that this actually holds because, as you can see, we start again at A and end up at A. So when you go from A to B here, the potential rises to E, and between B and C it still stays C because there is no circuit element. Now when you go from C to D, it drops by IR, and between D and E there is no potential change. And then when you go from E to F, there is a drop by I capital R, this distance here, and you end up where? At F. Now F should be at the same potential as A because there is nothing between them. So if we assume that A started, the potential of A was 0, then this should end up again at 0. As you can see, this is equal to this plus this, or this plus this plus this is equal to 0. Okay, this is the loop rule. It's easy to apply, but just keep in your mind that this is actually a reflection of the conservation of energy. The energy, potential energy, electric potential energy provided by the power supply is equal to the potential energy, to the thermal energy dissipated in the internal resistance and that in the load resistance, as we have shown before.